All right, welcome to Lecture 7. Today we're going to go over the concept of maximum likelihood and kernel density estimation. So, previously we learned several of the probability distribution that are very common and you guys probably have seen before. These are the 7 of them. For these distributions, the truth is that we got really lucky because simply by knowing the mean or the variance, or sometimes we need to know both, then that happens to be the theta term inside a function. Once we know theta, we plug it into the function, then we have the whole function. So for these particular cases, it is really easy. And it is lucky that they happen often enough in real life that they're useful. However, mean and variance is not necessarily always going to be the theta, right? There are lots of functions out there that you find the mean and it's not equal to the theta. And for these, right, then the question is how do you then deal with like really, really complex functions? You still want to find theta so that you know the probability distribution. How do you go about doing that? So that's the topic today, and the method is called maximum likelihood. So let's talk about independence. We previously went over probability, and we went over the concept of conditional probability. The conditional probability is the joint divided by the marginal, and when we move this over here, when we do that, that means that means the joint is equal to the product of these two. The concept of independence comes in when you know x, it doesn't change the probability of y. If that's the case, by knowing y, it doesn't change the probability of x. This means that you can just cancel out y because the probability of x doesn't get changed by knowing y anyways. Therefore, when we talk about independence, it is just the probability of x equal to the probability of y. And this is the definition of independence. Now, there's a common assumption in with data is that the assumption of IID, which is independent and identically distributed. This is essentially saying that when you collect samples, the result of the sample, one single sample, is not going to impact the result of another sample. For example, if you're collecting height of 1,000 people, person one and person two's height probably have nothing to do with each other unless they're related. So, assuming they're not related, then their height probably have nothing to do with each other. That's what we mean by independent. Knowing the height of this person will not tell you the height of the next person. And identically distributed means that these heights, all these people you're going to collect, all came from some distribution that we don't know what the distribution is. We just make the assumption that they all came from some distribution. Okay, so often when we collect data, we need to make this assumption in order to basically keep going to do a lot of the math. So IID very important. So, given that you know that what the IID is, let's talk about Gaussian distribution. This is one single Gaussian distribution. We've seen this multiple times by now. Okay, so the probability for x means you simply plug x in here, and you have the equation. You have the result of the probability, and you can then do the integral essentially. However, in order for you to have this equation, you need to know two more terms. You need to know the mu and you need to know the sigma. Okay? So without knowing them, then you don't know the equation. Now, if we just collect one single sample, right? This is the probability distribution that describes that sample. However, if we collect 1,000 samples, this means that we have sample one, sample two, so on and so forth, all the way to sample 1,000. If we have all these samples, then the probability of the first sample, second sample will be described by these equations. So there are 1,000 of them. Now, if we go back to the concept of independence, right? If you have probability of x1 x2, if they're independent, that means it's equal to the probability of x1 times the probability of x2. So over here, we have 1,000 of them. Therefore, it's probability of x1 times probability of x2 all the way to the probability of 1,000. Okay? And now this means that the joint probability distribution is simply the product of all of them, right? You're going to multiply all of them together. Notice the joint probability distribution is simply probability of the first one times the second one, all the way to the 1,000. And this is based on the assumption that they're independent, right? They're this one and this one, the height of each person are independent from each other. And we can shorten this by writing this here, right? So this right here is saying you're multiplying x1. So this is the multiplication product symbol, x2, and all the way to the probability of x1000. Well, since we don't want to write this all the time, we're just going to write x, which x here is going to denote probability 1 to 1000. So the probability of x is simply represented by this equation here, right? This is the equation. Now, this is one single equation. This is describing not just one, but 1,000 samples, all the samples that you collected. Okay? We still have a problem. Once you have this 1,000 samples, we don't have the equation unless we have the mu and we have the sigma, right? So at this point, you need to identify what is mu and sigma. Okay? Previously, in the last class, we identified mu as just the mean and the sigma, right? So you could calculate the mean and the standard deviation and plug it in. However, in this particular example, we're going to assume that we didn't know that. We didn't know that, right? Like I told you in the beginning of the class, there are many, many, many functions that the parameter are not the mean, not the mean. And remember the point of today's class is how do we deal with this, right? I mean, today we could have used a very, very complex equation. Then like it would really demonstrate the point. But it's easier to use a simple equation. So once again, here you're going to assume that we don't know how to calculate the mean and the sigma. Therefore, if the previous technique is not available to us, how do we go about finding mu and sigma? Okay, so that's the point. That's the point. Now, well, well, what would happen if we just make a random guess? Let's start by saying that we just make a really really bad guess, right? So here's an example of a bad guess. The real data is here, but because we made such a bad guess, the distribution is really here. Okay. Now this means that we are really really off. And what will happen if we calculate? Let's say we have a sample here, right? This is a particular sample. This sample, which is 1.8, based on this probability distribution, the probability of this sample would be very, very small, like basically zero. The probability of this one will basically be zero. Basically, the probability of every one of these points would basically be zero, right? So this means that when we are calculating the probability of all these data, right? Remember, we have the join. It will be the probability of the first one, which is very small number, probability of the second, very small number. So all these very small numbers multiplying with each other, leading us to a very, very small number. Okay? So if we made a bad guess on the distribution, this is what's going to happen, right? You're going to have very, very, very small joint likelihood. If you made a bad guess of x and mu, and you start plugging every single x in here, and then you have to multiply the probability of every one of them, the resulting probability is going to be tiny. Okay. Now, let's look at a different example where we made a better guess. So this is an example of a bad guess. This is an example of a good guess. Well, not a good one. Let's use the word better. This is the example of a better guess. So we made a better guess here. Now, the exact same sample would have been zero, well, basically zero, at a bad guess. But over here, it's actually a much, much larger number. This is also much larger. This is also much larger. This is all these are much larger, right? So you can then see that now that we have a larger number and a larger number, the product of all the larger numbers multiplied together will give you a much, much larger number as well. So, from this observation, you can see that as you make better and better guess towards the real true distribution, right, then your joint probability distribution is going to be the highest possible, right? So based on this observation, if this equation is our joint probability distribution, if you were to find the theta 1, theta 2, or the mu and the sigma, whatever you want to call them, theta, these are the unknown variables, theta 1, theta 2. If you were to find those, that maximizes the likelihood. That would be equivalent to finding whatever theta 1, theta 2, such that the probability will fit perfectly, right? When it fits perfectly, that's when the probability are maximized. Whereas when you have a bad guess, your probability are going to be very, very small. Okay, so this is the intuition of why maximum likelihood works. Maximum likelihood is when you simply have a distribution. You have a distribution, a joint. You have a joint distribution, and you want to find the thetas. To find the thetas, you simply maximize the likelihood. And when you maximize the likelihood, you can see from here why it gives you a much, much better guess that fits the probability distribution. Okay, so that is maximum likelihood. Now, let me show you a video. So, with maximum likelihood, if you know how to take the gradient, you can also run gradient descent. So, this particular example, you're trying to maximize it. So, what will happen if you're to run gradient descent step by step? Let's take a let's take a quick look. Okay? So over here, I programmed this for you guys, a video. This is basically, you can see right now, is the starting point. So we made a bad guess. As we do gradient descent over and over again, this starts doing better and better and better. So let me play the video. You can see that every single step is doing slightly better, right? As you come up, maximizing the likelihood. Now, there's a difference between what we're doing here and when we do minimization. So right now we're doing maximization, right? Previously we're doing minimization. When you're doing minimization, remember, if the gradient is going this way, you're trying to minimize, you have to go the opposite of the gradient, right? If the gradient is positive, you have to go negative, go in the negative direction. This means that if your W now must subtract, this is the negative of the gradient. This is if you're trying to do minimization. If you're trying to do maximization, then you're doing the opposite, right? Whatever the gradient is, you're trying to go higher, right? So whatever the gradient is, you have to go the same direction. Therefore, W next must be plus. So that will give you maximization. Okay, so when you're running gradient ascent, not descent, ascent, which goes upward, you have to be cognizant whether you're going upward or you're going downward. Okay, so this particular code, here's the YouTube video I just showed you guys. I wrote the code on how to generate this. Here's the code, and over here I basically have the Gaussian, right? And then in the Gaussian, I formed the joint likelihood. Joint likelihood. You want to make sure you study how I got this. You, you want to be able to get this. Now, I use the log likelihood, and in a little bit, you're going to see why taking the log of the likelihood is equivalent to the likelihood itself. I'll show you that in a little bit. And then, with this particular example, I just use the automatic gradient. And by using the automatic gradient, it found the gradient for me. And what I did is then cogradient descent. Okay, so now I want you to notice that what I did is I made the log likelihood, I made that negative. Okay, so what that means is what that means is if this negative is here, then I'm minimizing. I'll show you why in a little bit. Why, if you make your objective a negative, then you minimize. Okay, so for this particular example, it is still minimization, and I'll show you why. So you want to take your time, go over this code, and make sure you understand what's going on. Okay, all right. So in summary, you have some data, right, with some distribution p of x. You don't know what p of x is because like it's the parameters in there, the theta is not necessarily the mean or the variance, right? You don't know what that is. Therefore, if you do know, then the problem is solved. But if you don't know, then you have to use maximum likelihood. And you can solve it two ways. One is if the function is really, really simple, then you can take the gradient and set it to zero. But if the function is complicated, then you have to use the gradient descent with what I just showed you so that you eventually reach a really good solution. Okay? Okay. Now in summary, if you use maximum likelihood, you can solve it. Oh, no, I actually just talked about this already. All right. Next thing I'm going to go over is bunch of rules. This rules will make some of the things we do make sense. Rule number one for maximization minimization, right? If you were to minimize a function, that's equivalent to minimize a constant times the function. Notice this in blue and constant times the function is in orange. Notice that the solution x that makes the function as small as possible is the same. Okay, so when you multiply by a constant like alpha or 3 here, right, the solution is the same. You can just ignore this and you will still get the same solution. Second, when you add some kind of constant, notice how when I move this up, right, the solution for the minimization is still the same. It's still the same location that you will get the minimum. Therefore, the minimization of a function plus some constant, you can just ignore that constant and just do the function itself. Next, minimization if you take the log. If you have a function and you take log of that function, this means it will look something like this. See the orange? When you do that, the minimization is still the same. Therefore, when you take log, that's okay. That is okay. So the solution is also the same. Next one, when you're doing maximization, which is what we're doing here for maximum likelihood, if you that's equivalent to finding the minimization of the minus function, right? So you have this. If you turn it into a minus, it becomes this. So one is minimization, other one is maximization. Conversely, if you start with maximization, you take the negative of that, it becomes minimization. Okay? This is why in the previous code that I put the likelihood function as negative, and therefore I still solve a minimization problem. Okay, so these are the log rules and tricks you need to know. Log of e, we're going to assume log here is base e, okay? It's base e. So log of e is equal to 1. Okay, so log of e to the 4, this is simply 4 log of e equals to 4. Okay? Log of a product is the log of the summation of them. The log of subtraction is log of x minus log of y. These properties, you need to understand and remember them. Last one is you have a power to the nth power. You can move this power to the front, and they will be equivalent. Okay, so in this particular case, log of e to the x goes to the front, log of e, and log of e is equal to 1. Therefore, this is equal to x. Okay, so over here is another example. If we have maximum likelihood for exponential. So this right here is an example of an exponential distribution. With exponential, this is just one. And if you have 1,000 of them, an n number of samples, then you will multiply all of them, assuming they are independent, IID, independent. So if this right here is the joint probability distribution, then we can now start simplifying. Well, what does the product mean? It means you're multiplying all the way to x1 to xn. So you're multiplying them together. And notice that the thetas here are identical. So if you multiply theta n times, is theta to the n. And the power, right, terms, you can actually add them together. So when you add the power together, this is what you get. After this, we can, instead of taking the likelihood, we can take the log of it, because taking the log gives you the exact same solution. So now that I take the log, I can split the two terms out. If I split the two terms out, right, I can split, remember, xy, log of xy is equal to log of x plus log of y, right? So that's log of x plus log of y. So now I have two products and we split them out, just like here. So after we split them out, well, we can move the n to the front. We use that property. And e disappears and we can move that to the front. Therefore, this is the result we have. This right here is a simplified version of the log likelihood. Now, next, to take the derivative with respect to theta. The derivative with respect to theta is easy here, just this. The derivative with respect to theta, you just cancel that out, and you end up having this. And it turns out that this is so easy, we can set it to 0, right? When we set this to 0, we end up getting this expression where we can move this to the other side, and it shows that 1 over theta is equal to ex, which implies that theta is 1 over e to the x. So 1 over the average value. This is the same conclusion you guys learned from the previous lecture, that for exponential distribution, you can use maximum likelihood. And through maximum likelihood, it actually arrives to the same conclusion as we did previously, right? Which says right here, like if you take the average, it's actually 1 over theta. Okay. Now that we've seen maximum likelihood, like we've done the histogram method to get the idea of the probability distribution. We also just use the mean and the variance method to essentially get the probability distribution. Now we learn maximum likelihood. Okay, so these three are the ones we've done so far. The very last one, and I will argue the most powerful one among these, are called the kernel density estimation, KDE. This is the most powerful because you are no longer restricted by a function, right? It doesn't matter what the shape is. It could be something like this, right? It could be any single shape. And using KDE, you will be able to get the P of x, the actual function itself, for any shape. That is how powerful KDE is. Now, its power is coupled by the fact that it's actually really, really easy to do KDE. To do KDE, you need to understand how histograms work. With histogram, if you get a sample, you put a block there. You cut another sample, you put another block. And if you get the same sample, you put yet another block, right? So you're stacking blocks. You're constantly stacking blocks in a histogram. Now, with KDE, instead of stacking blocks, we stack Gaussian distributions. So, if we have a Gaussian distribution, let's say we use this. These are the four samples we got. The first sample says that it's at 1. We put a 1 here. And then the second sample is 1 again. We stack it up. Now it's a big one. The third sample is at 2. So we put a Gaussian distribution center at 2. And then the fourth one is a Gaussian distribution at 3, 2 and 3. And there you have it. This is the distribution. With this distribution, every single time you add a Gaussian, right? So this is a Gaussian distribution. So the way you would write Gaussian is this. However, this is a very cumbersome equation. Very often, we simply write this mu and sigma square. Okay, so by knowing the mu and sigma square, we basically have the function. Like, so this is the mu, this is the sigma square. So my point here is if you um, have four samples, the first sample is 1, you would put first Gaussian. Am I doing this right? First Gaussian, center around 1, and then standard deviation of some value. You pick the value ahead of time, right? And then the second one, you'll do it again. 1 again, sigma square. And then the third one, 2 sigma square. The fourth one, I'm really doing a bad job for this symbol. I should look up this symbol. Maybe it's like this. Yeah, it's a special symbol. I'll look it up and I'll correct it some other time. It's maybe like this. No, it's definitely something like this. Anyways, and the last one is 3 sigma square. Okay, and then because you have 4 distributions, you need to divide by 4 because the area of this is 1, the area was 1. So the area of this right now is 4. And you can't have the area to be 4. It has to be 1. So you got to normalize it back down. Okay? So you're averaging all these together. And there you have it. This right here is the KDE. Now, depending this just you pick this. Depending on value you pick, if you pick a small value, you end up getting a really sharp distribution. But if you pick a slightly larger one, notice how this is smoother. And then if you pick an even larger one, you can make the function look really, really smooth. So depending on the data you have, if they're really sharp, you basically look at the histogram and see which one fits better. Okay. So ultimately, this right here will give you the P of X. Let me see if I wrote this out somewhere. Yeah, I wrote it out right here. Right. So the actual function itself will be written as, notice how the mean is equal to 1. The mean is equal to 1. The mean is equal to 2. Mean equals to 3. So I stacked 3 of them and then I averaged them together. Okay. This is so when you want to find the probability of x, you simply plug x into every one of these, add them up, take the average, you have the solution. This is the function here for that very, very simple one. You can imagine that if you have 1,000 samples, then you have 1,000 equations. So KDE is powerful, very, very powerful. It's simple. But you end up having to use like 1,000 equations. So simple. So that's the downside with KDE. The function itself gets really, really complicated. Okay. Over here, this right here is the code that basically generated this. Okay, so remember I had the 4 points. They were There were, what were the 4 points? Did I write it here? Mean of one. So it's, yeah. So I have mean of one, mean of two, mean of three. So the first Gaussian, I use mean of one, mean of two, mean of three. So so this right here is probability density function. Okay? When I plot this out, you got this right here. So with very complicated functions, you can still get basically any shape you want that fits the data really well. That is the power of KDE. Okay. All right. So for the rest of the class, you want to essentially find and load the file, time until phone drops. Time until phone drops. This file consists of 1,000 individuals recording the time where they first dropped their phone, resulting in some kind of damage. So the time is in terms of years. So 1.6 would be 1.6 years. You're going to essentially see if you can solve these. I provide the solution for you. Here's the link to the solution. Hopefully, hopefully you'll be able to do it. Definitely don't look at it first. Try it yourself first, and use my solution as a reference. Okay. Now, if you finish that, the very last one is for you to essentially perform kernel density estimation on this distribution. This is called a chi-square distribution, and the red one, is essentially the KDE solution, and you should be able to get something pretty close to the red. Okay, I think that's the class. I'll see you next class.